So here we know that if this is the true value of the population percentage, and we estimate it by the sample percentage, then what do we know? We can get lots of different possible values for this, depending on which sample we happen to get. But on average, they're plus or minus 1 standard error from the population percentage. How often are they more than 2 standards away from the population percentage? Sorry? 1 over 2 squared, yes. All right, so, okay. Is that up on the screen? Good job. Okay, right, so Chebyshev's inequality says that the probability that the sample percentage, which we're using the symbol phi, so let's use that, phi minus the population percentage p is bigger than or equal to 2, is equal to 2 times the standard error of the sample percentage, is less than or equal to 1 over 2 squared, right? Okay, in general, chance that it's more than k standard errors away is at most 1 over k squared. Okay, so chance that they differ by more than k SEs is no bigger than that. What's the chance they differ by more than k times a half over root n? Let's go ahead and put an f in here for grins. This number, f times a half over the square root of n, is that bigger or smaller than the standard error of the sample percentage? It's at least as big, if not bigger, right? So if the chance that this difference is bigger than this is at most 1 over k squared, what's the chance that it's bigger than this? Still can't be any bigger than 1 over k squared, right? 1 over k squared is still an upper bound? Okay. So what I know is the chance that the sample percentage differs from the population percentage by more than k times this bound is also no more than 1 over k squared. In fact, probably smaller, because this was already an inequality, and this is now plugging something even bigger in as the threshold. Okay? So this is very conservative. Are we together? This more or less? Okay. So if I know that the vast majority of the time, so if I put in a big value of k, like 3, then I know that 8/9 of the time, at most 1/9 of the time, the sample percentage is going to be further than 3 times this away from the population percentage. Well, let's suppose that, so let's draw this again. Here's the population percentage p. And let's say that this is now p plus or minus 3 times f times a half over root n. So this is 3 times f times a half over the square root of n. And that's p plus that. And this is p minus 3 times a half, times f over root n. Okay, so what do I know? I know that 8/9 of the time, my sample value, phi, is going to be in here somewhere. And at most 1/9 of the time, it's going to be out here or up here. Right? Okay? So if I'm in one of those sort of 89% of the time samples where the sample percentage is in this range, what happens if I take the sample percentage and I go up and down from the sample percentage by this amount, 3 times f times a half over root n? Well, if I'm if I'm closer to p than this limit, then when I go down by that amount, I'm going to trap p. I'm going to go up to something like that. I'm going to go down to there, and I'm going to cover p. If I'm in here, then if I go up and down by this amount, I'm going to include p and include some junk up there, right? And if I'm down here, again, if I go up by that amount, I'm going to include p, and I'm going to include some junk down here. Right? So whenever the sample percentage is in this range, an interval around the sample percentage of this width is going to include the true value. Okay? If I'm within 3f times a half over root n of the truth, then I'm within 3f times a half over root n of the truth. And so it doesn't matter whether I measure from the truth to the estimate or from the estimate to the truth. If I'm within that distance, I'm within that distance. Okay? So if I report it as my interval, the lower end point is this minus 3 times f times a half divided by the square root of n, and as the upper end point of the interval, phi plus 3 times f times a half over root n. This is a random interval, right, because it depends on phi, and phi is a random number. Phi depends on the sample. It's the sample percentage. Okay? So this is a random interval. It's centered at phi. It goes down from phi by this much. It goes up from phi by the same amount, right? Okay? So this interval is random. Sometimes it's centered at a point that's up here. When that happens, the interval is going to miss the truth. Whenever it's centered at a point in this range, it's going to include the truth. So whenever it's centered at a point in this range, it's going to cover the true parameter value. So this is a confidence interval for the true population percentage p, and the confidence level associated with this, the sort of the fraction of the time that that interval is going to include the truth, is going to be at least what? Right? It's at least 8/9. At least 8/9 of the time, the sample percentage is this close to the population percentage. Whenever that happens, this includes the truth. Okay? Some of the time it isn't, and then it doesn't include the truth. Let's do a little. Okay, so what do we got? We have a 0, 1 box. In this case, there's 3 zeros and 3 ones. And we're going to sample without replacement. We're going to take a sample of size 3, and we're going to go up and down from that by 2 times our bound on the SD of the box. Sorry, 2 times our bound on the SE of the sample percentage based on the bound on the SD of the box. And in fact, in this case, the box does have 50% zeros and 50% ones, and so that bound is sharp. So if we do this, and we take a sample, this time, when we went up and down by twice our bound, that interval missed the truth. This time, the interval included the truth. This time, it included the truth, et cetera. Right? So whether we include the truth or miss the truth depends on what value we get for the sample percentage. All right? So if we do this over and over and over again, this is going to include the truth most of the time. How often do we know it's going to include the truth? Okay, if we're going up and down by twice our bound on the standard error, chance that things are beyond that is at most 1 over 2 squared, right? 1/4. So this ought to include the truth at least 75% of the time. What actually happened, it included the truth 88.5% of the time. Okay, so it's conservative. It includes the truth at least as often as we claim that it will.